So I'm going to talk a little bit today about something which I firsthand experienced. So before I rejoined Drepper, I was working in Wall Street, and people leave in many places, just taking solutions someone else has come up with and utilizing them. But also, I don't know whether you know it or not, so Red Hat is really an infrastructure company, so we are building pieces, and that's believe that the best person to actually come up with the final solutions are those who actually have to use it in the end. And I want to try to make a case for it and to that this is the right approach also for machine learning work, despite what you might believe right now because of all the press and all the success stories that you hear from all over the world and from people who have the reason for you to believe that. I will go along with this picture, which I at some point in the past drew up, which is depicting the workflow of a normal machine learning project. If you go along with this, so I'm not sure how many are actually practitioners of data scientists and so on. Okay, few, but not that many. So I might have to go into a couple more details there. So let me explain it therefore. So in general, what we divide the practice of actually getting to machine learning models and actually utilizing things nowadays is that we first collect data, which is the most important aspect to it. Then the biggest part is actually cleaning up the data in general. So which means that the raw data by itself is oftentimes just missing data. It's not the right kind of data. For instance, if you have textual data, you want to only extract a certain portion of it, so not the entire strings, etc. for these kind of things. And make it then also available in a form which a program can easily digest. So usually, ideally, this consists of a table of some sort, perhaps multiple tables, which have nice columns with the different values which you're actually looking at, trying to use inside the modeling. The rows are individual data points. This by itself is oftentimes completely ignored in the workflow. I usually tend to say that this is at least 60% of the entire work of a modeling process, and therefore should not ever be discarded. Then we have what follows is the good practice of how do you actually make sure the model does what it's supposed to do. So you're not only training the model, you're not getting to the parameters which are describing what you later on will deploy perhaps as the potential model itself. But you also have to make sure that you have some independent way of verifying that the data actually also supports the model in the end. This usually is done by splitting the data into sets, the training set and the testing set. This is the simple version. In reality, you should have 3 sets, but I'm ignoring this at this point. And the training set by itself must be completely, in general, be independent of the test set. Only under certain circumstances, when you have very, very little data available, should you ever mix the two of them. But in general, you should assume that you have a training data set which is independent of the test data set, and the training side with the development to come up with the model parameters and so on should not ever have see any of the test data by itself. So you have this nice split which you try to depict there. So as a first step, as a fourth step in this case, what is most people consider the most important one is saying, well, how do we actually develop a model? And we have to have first ideas what kind of model you want to deploy. So it can be as simple as normal regression, but it can be also sophisticated stuff like neural networks, which are all the rage. And this usually is a fixed method how you use this kind of data. So there are certain procedures how to approach this mathematically, but how this actually is implemented can vary very widely. This is not really a simple step by itself. The fifth step resulting from that is you have to actually test the model. This is where the second split up data set part comes from. So the test data set is data which has not been seen by training, and therefore if you input the test data into the model, which is trained based on the training part of the data set, you get independent results. So this should be a somewhat good reflection of how the model will actually behave in the real world once it gets deployed. And then it's up to whoever is doing the modeling to decide what is an acceptable model. So how many divergences from whatever the testing, the output for the testing data set, how many divergences are actually acceptable in these kind of situations. So if it's not good enough, well, we have to either find a completely new model, we have to refine it, etc. And this might actually not only going back to the training side, we might actually have to gather new data, we might have to utilize existing data differently and so on. So it's a somewhat involved issue. And only if the model has been good enough do we actually produce a model description where we can actually specify in detail, this is the model itself, these are the parameters we are using for this, and this model then we can put into production. We are calling that inference, and this is what this vertical line there, the dotted line is representing. So on the left-hand side we have the training side, on the right-hand side we have the inference side, the runtime side. And there we don't get the data from pre-canned data which we have collected before. And this is now the real use where we have new data coming in, probably in real time, but perhaps also from other databases in batch forms and so on. And we are utilizing this data, the model, and we are getting out some results. So this is the normal workflow, ideally. So this is representing what is called supervised learning, but in a slightly adjusted form can also be done for unsupervised learning. And in some way or another, this should be implemented by everyone who is actually practicing data science or actually doing machine learning. So I'm breaking these steps down now into the individual components, and I'm going to talk about that. But before I do this, I want to just point out one thing. This is, yes, there are programs out there which are promising you to do all these things at the same time. So they're promising to clean up the data for you, they're doing the training, you just have to point and click with something like this. But, well, they never really work 100% of the time. And if they don't work, then they're almost impossible for you to fix it. So, as I said, a company I work for is infrastructure provider, so some of you might have heard about this thing called Linux. So I actually wrote large parts of that back in the day, so my background is computing. And I believe strongly in the philosophy of the Unix world, where we have small tools which are doing one job really good, and we're stringing them together. And this is what you will find in this talk as well, which I'm promoting. So, for instance, for the data engineering side, so the cleaning up of the data. So there are these big programs which are promising you to do all these kind of things, and at some point maybe we are getting to the point that we can get some automation in there, where we don't need to use it to individually tell, oh yeah, do this transformation on this column in the input file, on this file, etc., etc. But in general, this is not so easy because there's such a wide variety there. So there are different file formats which have to be recognized and handled. So it can be as simple as a text file, which can be unstructured text, like for instance log files. It can be CSV files, which are text files, which have actually a record form. It can be then things like JSON files in text form. So it's really wide variety of this, and then knowing the recognition of what is what is really not that easy. So because then we have also the problem, how do we actually split the columns? So again, let's go back to the example of a log file. A log file usually consists for each of the records of one, perhaps 2 or 3 lines of code. So how do we split out the individual pieces, especially because in most cases the origin of these log files, the people who wrote this code don't really necessarily have automatic analysis of the logs as a goal by themselves. So this is mostly for human consumption, and that makes it very hard for the computer to do the right thing. So other things are, for instance, in many cases, you don't find it useful to have a single line, a single data item as a useful input into the machine learning algorithms. You might have to accumulate more than one line into this, and then what operation do you do that? Do you look at the maximum of the columns? Do you sum them up, or whatever other transformation you're doing there? So there are many, many different ways to actually do this, and what you will find out there are programs which are giving you some form of GUI. So I'm deliberately not naming any names in this talk in general, so I'm trying to not offend the people who are writing this piece of code. But it will look something like that, where they give you GUI where you can say, oh yeah, I have this thing now here which represents well, take this column and split it up at character 10 and up to character 20, and that's my new field. And you can string these kind of transformations one or the other, you create something. Well, the bad thing about these kind of things is, first of all, if the transformation you want is not there, well, how do you get it there? The second thing is that if you, how do you control whether this is actually doing what is going on? How do you get to the intermediate steps? So usually this kind of thing, they're just depending on the fact that you have to trust them to do the right thing. Or you have to do it in very, very small steps individually, but then why bother with something like that? So on the other hand, there are other tools which can do all these operations nicely, one by one if you want, with a little bit of scripting, as we call it, so a very high level description of the transformation especially in the Unix world, but this has also Go and NDI there. In the other computer environments, we have text transformation tools since day one, and they're pretty easy to use. The regular expressions are now widely used mechanisms recognized, and well, they're the perfect tool for these kind of things. The other problem with the data engineering side is that people found, oh yeah, I have so much data to do, so I need to do something about accelerating the whole process. This is where all these MapReduce stuff came in. So a whole bunch of years back, this was all the rage. People have this, oh yeah, I can schedule these massive amounts of jobs or massive jobs which can transform gigabytes of data by just writing a little bit of code here and tell it, oh yeah, do this little transformation, then pass on the results to the next one. So what really happened there is that you have, every single time you have a snap, so this picture is supposed to represent, so you have these individual snaps and you have perhaps multiple concurrent workers working the same thing, but every single output which comes out of this is serialized, and the inputs have to be deserialized again. And the whole thing also oftentimes has to be transported from one machine or in one network to the next one, which creates enormous inefficiencies. We were known from just the programming language used for that, so I'm a big hater of Java, and this stuff is all Java written, so you cannot expect performance from that kind of stuff. So the biggest thing is you cannot read it, but there's a URL there, so at some point you can get the slides and you can look at this. There's a guy who, and I like this because I did exactly the same thing to my colleagues back in my previous job, where they took publicly known, well, at some point they said, yeah, here's something which people used MapReduce for, and he replicated this with a simple awk script. And guess what? The awk script was 200 times faster. So just because it's possible to do these kind of things doesn't mean it's right. There are so many tools out there to do these things, so just learn about them. Don't believe this hype in these next big thing. Oh yeah, because Google did MapReduce, well, we need to do it too. No, oftentimes, or very often actually, this is not the right answer to that. So text transformation is a well understood problem, and why not use it? So just use the tools which we have available. So on the training side, it's quite a different scenario there. So the problem behind at the training is not necessarily that we don't need to have the tools and so on. We have specific mathematical methods which we have to follow, and there's no shortcut around these kind of things. We have to perform certain mathematical actions and so on. The problem is that usually you don't really know what are the exact learning parameters which you have to specify. Oftentimes we don't even know ahead of time what kind of algorithm we want to use. And therefore the premium in the training phase usually is the turnaround times, which means that the data scientist sitting there and trying to figure out how do I develop a model itself is an iterative process. So they're having an idea, they're trying it out, and then they have to wait until they get the result. So if it's something as simple as a linear regression, yeah, the computer can do that within a second or a fraction of a second probably from those data sets. But if it's something more complicated, so not only neural networks, but the other techniques such as clustering or support vector machines and these kind of things, they're taking a long time. Sometimes not hours, but days or weeks if you want to do this. And if you imagine if then the result of the training is, oh yeah, I have to repeat this because my result is not the expected one, tweaking it will take again that much time. So the most important part actually for this is the efficiency of the training itself. This is how we arrived at the current situation where everyone really believes that, yeah, every data scientist has to have a GPU in their machine, or have it available for them, which to some extent is the right answer, because GPUs or similar accelerators, so Intel has Google has what is called the TPU, tensor processing unit. They are really, really good at one thing, at linear algebra. And mostly actually dense linear algebra. It's a very important difference to sparse linear algebra. So we can do vector, matrix, tensor computations very, very efficiently, which is good in some respect because some of the problems we have been focusing on, or not problems, one of the solutions we have been focusing on last year are neural networks. And neural networks are nothing but tensor multiplications. So it's a very easy thing to accelerate, and therefore it's a really nice reason that we now have these many accelerators available for everyone. But these accelerators are really particularly bad as nonlinear code. So code where you actually have something like an if thing in there at some point, which, if we are leaving out neural networks, every other mechanism has in there. So which led the data scientists to hope that neural networks, and especially CNNs and RNNs, are actually a universal solution because anything else they cannot handle, which is actually not true. We know it's not a universal solution. But we're treating them like that because we don't have the means to do that. Do anything else. So the other problem related to this is that we believe, or many people really believe, that to get the highest performance out of it, we need to use the tools exactly as they come from the appropriate vendors. So hardware vendors in these cases. So the picture is about one vendor, but there are actually quite a few of them. And they're not only providing us with the hardware itself, they're also selling us their software environments. So in this case specifically, we're talking about NVIDIA. NVIDIA, as you might have known, has a software which comes with this called CUDA. And they have been telling developers, oh yeah, you always have to use CUDA for best performance. You're writing your code with direct CUDA interfaces and so on, and it all works best. Well, the thing most developers at this point don't realize is that you are tying your future to one single vendor. What if you want to deploy it another thing? For instance, there were quite a few people who wanted to try out the competing accelerator technologies, for instance, from Google and so on. Well, guess what? That code has to be rewritten. So these kind of things, in my opinion, and also this for many other organizations, they have absolute strict rules to never ever write code so that you're tied to a single vendor. even if this means there is a little bit of additional inefficiency. So instead of having this picture, we actually have to have something like that, where the actual technology which is used, so in this case, for instance, CUDA in the previous one, is abstracted out from the application. So we have actually a higher level interface set, call it framework in this case, which is then potentially utilizing the lower level ones, like the CUDA interface. But they could also use other interface libraries, which can use other pieces of hardware, or they can also utilize the local CPU, etc., etc. So this is the only way to actually prevent this kind of thing. So as I said, this is not just corporations and so on, so specifically all the government-funded organizations have to follow these kind of things as far as I know. So my experiences are mostly in the POS systems, but I think in U systems it's in the same way. You cannot tie your future to one single vendor in this case, and this is how you can potentially do this. The other thing is then, well, you should also not necessarily think about the frameworks in the way that you want to have one single framework for these kind of things, because not everything is done equally well in each of the individual frameworks and so on, and not the predominant framework, for instance, is perhaps not choosing the right or the best implementation, but instead it is chosen, well, perhaps for political reasons, or for reasons which are not really really visible to you. So there are, for instance, we know TensorFlow, for instance, is one of the possible implementations there. Everyone is talking about this and utilizing it and so on. Yes, it's one possible way, but this should not mean that you should tie everything to this perhaps one single framework. There are others out there. Not only that, so we have now systems, so I'm just mentioning Julia in this case, it's a programming language, which was deliberately meant from the beginning to have really good support for writing these algorithms by themselves, so from the get-go, without additional big frameworks necessary. The implementation brings it along with it. And perhaps we don't need any expensive frameworks for that. It also has support for utilizing accelerators like CUDA and so on, all from the language itself. And for me, from systems guy and also high performance interest, so I personally think that every organization should also have a second look at actually trying to write the framework exactly as they need it themselves. And the right thing for that is to use C++, in my opinion. And this scares people because most people don't really know what C++ today is. They have this picture of C++ from 1998, the first standardization of the standards in mind. It's wrong. That's not what C++ nowadays is. So it's a modern programming language with all the features which are in there. But in addition to that, it's fast. And we have access to the hardware. So, and how easy it can be, so there's another URL, that's one of my GitHub accounts, which is a GitHub repositories. It's a tiny little example for a neural network. So the end result is that I can represent in modern C++ the definition and all the code associated with a dense neural network in one single variable declaration. Everything else automatically falls out of it. So if you write your frameworks well, you not only get complete control over it, right? Perhaps you don't even have to write this, but you can take advantage of these kind of things, but also you have complete control over it for future deployment because, well, guess what? The C++ compiler will be available for every single machine out there. And all the underlying acceleration libraries on the devices have programming interfaces at that. Unlike, for instance, in Java, where you have to go through something called JNI to actually access something which is a little bit closer to than the virtual machine. Well, we don't have to do this in these kind of environments. And so you are in complete control of what you can do. And you don't even really have to know about what these accelerators are necessarily. So with modern C++ compilers, we can actually annotate just the code. So this is an example using something called OpenMP, how we can annotate C++ code and let the compiler do all the hard stuff of figuring out how do you use this complex piece of hardware. You're only, as a programmer, are telling the compiler, well, this is my job, and this is what I additionally know about the code. For instance, this can be executed in parallel, blah, blah, blah. And for instance, the modern GCC version, which of course is the one which I'm interested in because we're developing it, can target with, if I input this code in the C++ compiler, I can tell it, well, generate code for an Intel processor, for an NVIDIA card, for an AMD card, and for an Intel 5, all at the same time, perhaps even in the same program. And at runtime, the program will pick the best hardware available, maybe multiple of them. You don't have to worry about any of these kind of things. So just imagine these kind of things if you are tied to one specific example. So you cannot just swap between different machines with different pieces of hardware available. So this gives you a lot more flexibility when it comes to this. The other thing is then, which also plays along with this, why do you need different pieces of hardware is, well, maybe you happen to have a deployment in-house. So you have either a local cluster or your data scientist machine has a certain piece of hardware, but perhaps you want to scale out. You need to have, for short term, you need to host it somewhere else, either in a public cloud or in some other rented space, and the same hardware might not be the same, but you want to take advantage of it. You don't want to spend additional time actually targeting this. So this gives you a lot of flexibility when it comes to the actual deployment, whether it's on-premise or whether it's in cloud, it doesn't matter with these kind of programming techniques. But in many cases, you should also not forget the cost associated with this. So I just want to throw this in because there was another nice article from someone who actually did the math. The reason why these graphics cards are very much as a target for data scientists nowadays, it actually makes a lot of sense to give your local data scientists the best possible hardware they can get, because it might, from the cost, from the capex versus opex cost, it might seem that these cloud environments are giving you lots of flexibility when it comes to actually utilizing it and running it, and you might actually get those results because they also have GPUs available in there. So if you see this in the top right, if you look at the cost over time, it takes just, in this case, about 2 months to recoup the cost of a very expensive workstation as compared to the normal AWS node to overtake this. So AWS has a fixed cost, so unless you have very long-term commitments over many years, it's about this orange line, and you of course have a higher startup cost for if you're buying something, but the actual upkeep is very much less. And this gets even more interesting and more dramatic if you increase what is possible, the number of GPUs you're putting into a single system. In this case, the guy actually took a big AMD system, 1920X, so it's one of the Ryzen processor, and put 4 1080is and TIs, I think, in it, and compared this with the appropriately sized AWS nodes. So it takes just, I think, around 20 days to recoup the cost. So it might be that this machine by itself is not sufficient for most of the, or for some, not really, for some of the training costs. But if you ever look at the awesome power which you can get on a local machine where local disk access, ideally using lots of RAM, and at least through SSDs, and with a machine which has 4 of these 11 gigabytes, 250 watt cards on your machine, you can do so much compute on that that usually the data scientist has to think harder for the next program, for the next experiment he or she wants to do before this actually finishes. These are really awesomely fast by themselves. So I don't say that cloud deployments don't make any sense at all, but you always should reconsider how you actually do this And again, having a single instance where you don't have to swap data between different nodes and pay for data transfer and making sure all the data is consistent between the different nodes, as opposed to having everything on one single node, ideally all in memory, because you stocked up the machine with lots of RAM. This might actually make a lot of sense. And then we come back to how do we do the best high-performance computing on that? Well, you know my answer. You write your own code in C++. So testing is the next phase again. So I mentioned this beginning. So we take the model by itself. The problem here is really relatively small. So in general, it's not about the problem by itself. So the compute is not really that expensive. You're only doing one set of inference on the data sets, and you compare it with the expected output and do something about this. So the most important part is here to actually do it and do it right. So the speed problem is not really that relevant. So it's more that also on the training side, yes, you need the high speed, but for testing, not necessarily. What is more important is actually to do the analysis in the way that it actually works, and you can actually repeat, if necessary, the learning experience. So I mentioned at the beginning that I said in the previous section that I said the data scientist is choosing the next set of experiments, which is possible. If that could be possible. But in general, this what's called hyperparameter searching should also be automated. So which brings me to the point that we actually have already today relatively small pieces of software which can govern the whole process of the training and the testing phase. Because what you want to do is not just running the training and the testing and so on, and then doing a manual comparison. You want to record the results. And you want to ideally automate the repeat by saying, well, here's an algorithm that tells you about the next set of hyperparameters. And the reason for actually recording things is even more scary than just looking it up and finding the best way. One of the biggest problems which you will probably face at some point if you want to deploy these kind of models is that you might be blamed for having a biased algorithm. So we already saw this in the talk this morning where that some of the models might actually be fed incorrect data, and they might actually reach a conclusion which it should not have. If you don't have a recording of how you actually arrived at the model, you might get sued at some point, especially if you're from the US. So these kind of things are terribly important to do. So, and this is nothing new. So everybody who has at some point worked in academia, and especially in the research area, knows that this is exactly what everyone has to do in a research lab. That's a lab protocol. We just want to automate these kind of things. So there are projects out there, really smaller ones and so on, which can keep track of everything which is at the experiment running, including the testing, and some of them can even reschedule the training again with new hyperparameters, and some of them are also going to take advantage of the appropriate infrastructure on this. So perhaps you have multiple machines on which you can run them. So just saying this from my background, so this is infrastructure which I hope we will have something which you can easily use in our product, already built in at some point, so you don't have to look that far. But it's already out there. So there are nice projects, and this is a GUI for one specific one. It's called Secret, which is just a nice little GUI interface in your browser around something which happens in the database, and some scheduling software which does all these kind of things for you. Again, not a big monolithic piece which does everything. It just calls, it keeps track of which search you have done, but then when it wants to do some additional training, it just calls a process which does the training for you. And that process is completely independent. You are in the decide what it's supposed to do and what happens there. So this is exactly the way how this kind of thing should be done. So as I said, ideally in the end, we will have more automation there. So we will definitely want to have better decisions and automated decisions as to what kind of hyperparameters to search next for. So there's lots of research going on there. For instance, there has been lots of assumptions been made how we best trained neural networks. So just pick some somewhat random distribution initially and then use some form of gradient descent. But it turns out that we have nowadays gotten a lot of experiences with how we can do it perhaps better. So combine it with something called simulated annealing, and these kind of techniques could be built in nicely into an algorithm which can do these kind of things automatically for you. Like again, this should be a nice addition to the recipe system which does the scheduling. And Unix way, we are writing nice pieces of code which do as what is the one task good, and then they combine it. So next thing is perhaps somewhat, I would guess, the most controversial, I would say. So model creation. Oftentimes it's not broken out because many people assume that the way we are training the model, and or perhaps even the testing side, and the way we're deploying it should be identical. I would surmise this is absolutely wrong thinking. So we should actually have a representation of the model in some way or form. So this does not have to be just a gigantic binary piece which represents the matrices or tensors which are representing neural network or something like this. We need to have at least the possibility to have an alternative implementation. I'm going into that a little bit later, so we're talking about inferences. And there is actually a way how to do this. Quite a few years ago, someone came up with, or some group came up with something called PMML. Anyone ever heard about that? Okay, 1% of the people, okay, 2%. PMML is yet another description format. So here's an example. So this is the example of doing clustering on the well-known little data set, the nice flowers, which are everyone, the petal data set, which everyone knows about. This is a complete description of the model. So I can have a training part of the problem produce this PMML file, and then give this PMML file to the inference engine, which can be completely differently implemented. And it will work exactly the same. And I know that it works the same. If you cannot do these kind of things, if you cannot specify it like that, if you depend on the implementation to be exactly the same, it might mean that you're not replicating something which you think you're representing it as a model, but you might represent in addition to that some idiotic behavior from your implementation. So it's much better to rely on something like that, especially again, I'm going back to the legal liabilities. In some situations, you might actually have to represent this information. So for something like neural networks, this would not look as nicely as this, where we just have a couple of numbers which you have to represent. But it will represent, yeah, I have this many layers, each of these has that many neurons, column this way, these are the weight vectors, but it will all be in there. So it will be archivable for eternity. And in some industries, so again, I work in finance, the regulators require that for at least 10 years you have to be able to reproduce every single calculation you have done in the past. This is a way how you can actually preserve this information. So, which leads us now to the model deployment. Again, as that's the PMML is one possible way. I'm not saying that you have to do it, but I suggest something like that is a good way of doing this. So, the fact that most people say, yeah, you should use exactly the same implementation is really not the right one. So, we want to actually deploy it in a way which is independent of the input, but at the same time, we, well, actually have exactly the right representation. So we have a loader for this PML, for instance, which is easy enough to do. But more importantly, this must not be a one-time thing. So you cannot say, I'm training the model, and that's it for now. So forever, so I'm just using this piece here, and that's it. So this might be useful, for instance, if you're working in a marketing organization and you just want to run an experiment for a day or two, and at the end of that you will collect the data and the whole project is over. Okay, in this case it's a one-time effort. But most of the time this is not the case, and especially in regulated industries it will never be the case. In these kind of situations you have to make sure that you can reproduce this, but more importantly that you can update the model. So the deployment phase actually becomes part of the whole process of retraining the model, based, in this case, not on the data which we originally collected, but on new data. So the reason for that should be obvious. So if you have data which is stationary, so input data, so which usually means that over time it doesn't change. But then you can make an argument, yeah, perhaps we don't have to retrain the entire model. But usually data is not stationary. So for instance, if you look at the number of cell phones which get sold every single day, or month, or week, or whatever, and something like this, there is seasonality in the data, so which means that for the holidays, probably more are sold than during the, let's say, during April, just make this up. In addition to that, you might have a trend. Over time, it goes up, maybe it goes down at some point. So if you don't account for that and don't retrain the model based on the data which you collect in the most recent time period, you will get wrong results. So this means that the entire deployment phase is not a one-time thing. It must be integrated in the whole larger aspect of how you are actually utilizing any kind of model. And that again means that you cannot just write a program and just put it in production in the same way. It has to be done in a much easier way. So, which brings us finally to the inference phase, which is actually running the model. Here the problem, again, is not just that we want to have an independent implementation for the sake of having more than one piece of code. The main reason I would want to suggest is that the compute situations in which you want to deploy the model are often very different. So for instance, in some situations, so I don't know whether, how many of you have followed this kind of hardware, for instance, in situations where you want to deploy a model which is of direct use to a consumer, you nowadays can deploy it on a cell phone. So Google, for instance, has a special chip, or basically more directly an extension of the ARM chip, which it has in there. But that one has a completely different programming interface. So this is not the one which you want to use for training purposes, but if you have an independent description of how you run the model, this is easily doable. And so this can even go down to if you have, let's say, a light bulb or something like that, which can have a very small processor in it, but if the amount of input data and the rate at which you have to produce a new model prediction is very low, you can run a neural network or any kind of other statistical stuff, even on a terribly slow kind of processor at the low end. While on the other side, for instance, if you have, for instance, something like you're training a model which tries to predict outages in your compute network. Well, you train it on a certain data set, but then you deploy it. And if your deployment has 1 million machines, well, guess what? How much data do these kind of million machines are producing every single second? You cannot do it with the same type of machine usually you do the training on. So there you might actually have to scale it up significantly. So having an independence of the way you develop the model and the way you deploy it is not only useful, as I said, because you want to actually have a reproducible and explainable model, but also it gives you a lot more flexibility how you deploy it actually, and match the kind of compute power you have available for the modeling to the situation and not to what the data scientist has available or on which can be both best programmed. So we have, the picture there shows it on the left-hand side, that's an FPGA. So we can program a simple FPGA on a board like that, which costs perhaps $2 or something like that, with sufficient performance that we can actually have a really reasonably large neural network be simulated on this thing. And the whole thing then will run with less than 1 watt. So that's something which you can put thousands of them in your organization, which you could not possibly do with laptop-sized computers or something. So in conclusion, so you should really adjust the mechanism, the workflow of the data scientist to not just the needs of the individual steps. You should also have it with hindsight of the deployment phase. You should look at this, how do I develop over time? So what are the tools? Do I have control over the tools if I want to actually change something there? Because another aspect which I haven't even mentioned is, once you are deploying one of these big packages which are out there, there's a lot of training involved with that. Do you actually improve the cost for that? If you have to change things every couple of months or years, something like this, this is usually not such a good investment from my experiences. On the other hand, if you have these small little tools which you're controlling yourself or which you can oversight yourself, and get produced and they have been in use for many decades now, you can put them together with very little efforts. You can do transformations, you can do all the calculations there. The math behind the models is well understood. There are libraries out there that you can use. You just have to stitch them together with a little bit of effort. You're in control of every single aspect of this. You can explain the data if necessary, so you can represent it, you can store it, you can take advantage of new hardware when it becomes available. This only is possible if you're not relying on too many different big blocks where only one source can actually help you out with this. So